decomposition and moment problems. So this is a joint work with Mikhail Gabay, Figen Sokrat, Bernard Moura, and Cordian Rangnick. So this talk is organized as follows. So I'm going to start with the motivation and the problem setting of the tensor decomposition problem. Then I'm going to present the SDP formulation and the moment formulation for this, and also show the low-rank structure of this problem. Then I'm going to present some numerical results and finish with conclusion and insights on future work. So there are many problems in applied mathematics that lead to high-dimensional tensors. And for this talk, we are going to focus only on symmetric tensors. And one of the central tasks for tensor decomposition is to write this tensor as simple terms of rank ones, such as like writing our tensor as the sum of lambda I times vi to the power of d, and where r is the rank of the tensor. And this is useful because it's this representation is compact and structured, and also, however, finding such a decomposition is highly difficult because it's a nonlinear and non-convex problem. And the main question here is: can we represent this, formulate this problem as a convex optimization problem? And our approach is to pass through moment representation. So the main pipeline is to take our tensor decomposition problem, reformulate as a moment matrix completion problem, and use the semi-different programming to solve these kind of problems. And the use of SDPs here is natural because the moment matrix has this Hankel structure. There are the linear constraints coming from the tensor coefficients, and also there is the PSD constraints on the moment matrix. And also, for a tensor having R components, the associated moment matrix is expected to have rank equal R, and this motivates the use of low-rank SDP methods. Now we can go deep on this tensor decomposition problem. A symmetric tensor can be identified as a polynomial, and the tensor decomposition problem, it consists in writing this polynomial as a sum of linear powers. However, as I mentioned before, finding this decomposition is highly non-convex and non-linear, and the number of the moment matrix that is associated with this problem also grow combinatorially with the number of variables and with the dimension of the tensor as well. And the link with the moment problem is done via the upper product, which links the coefficients of links the polynomial coefficients with the point evaluation. So, for example, if we have polynomial in this form, and we do the upper product with any polynomial j, this upper product will equal to the j evaluated at the point xc. And so, if our polynomial f is written in this way, its upper product with any polynomial j is the integral of j with respect to the measure mu. And so now we can see like the tensor decomposition problem now is finding these measures mu, where some moments will correspond to some coefficients of the tensor. And here, if we take j as a monomial x alpha, for example, we can explicitly find a moment constraint, which is given by the inverse of multi-binomial coefficient multiplied by the coefficient f alpha of the tensor. And you can see here now our problem is finding such a measure, positive measure, such that there are some moments that can be obtained with the coefficients of the tensor. And for this, we introduce the truncated moment sequence y, or y alpha. And from this sequence, we are going to build the moment matrix. And then the SDP relaxation is finding this sequence, such that there are some sequences that are that are given through the tensor coefficient. And also we have these constraints on the moment matrix that we already created. And now if we look at the SDP formulations for the primal and the dual form, we can see here, like for the primal shape of the SDP, we have the PSD matrix is only X, and this is the main used SDP shape for the main solvers. And for the dual view, we have our coefficients now are becoming Y and the slack S. And the PSD constraint will be on S, and the structure of the problem will be integrated in this parameterization A star Y. And one of the questions that we can ask is how many constraints and variables do we have in each formulation? And in this example, where M here is the size of the moment matrix and M is the number of the moment variables, we can see here, like for the primal SDP formulation, we have more than 11,000 of variables and more than 11,000 of constraints. However, in the dual formulation, we have only 425 variables. And this is because the Hankel structure is already encoded into the parameterization A star Y. And as I mentioned before, if our rank, if our tensor has small rank, then the expected moment matrix is becoming also low rank matrix, and we are going to think or focus only on the dual SDP methods, where the slack S can be written in low rank format. And here our variable now is Y, where Y have P columns, and we of course expect that P is too small compared to N. And for these standard SDP solvers that are working with the full SDP shape, they are usually robust and accurate, but their performance depends on the size, on the number of the constraints. However, for the low-rank SDPs, they are exploiting this low-rank factorization, which lead to the reduction of the variables. However, now we will have a problem that is nonlinear and non-convex. And we are going to compare CSDP as a standard SDP solver with ManyDSDP, which is an existing implementation of dual low-rank SDP method for solving our moment problem. And before showing the numerical results, I want to show or present the adaptive rank strategy that is illustrated or introduced by ManyDSDP. And so the idea is to start from small p, which is the size of the matrix Y, and solve the low-rank subproblem in Y, and check after that the SDP optimality conditions. And if this current factorization is insufficient, so we need to increase P and continue the same process. And the main idea is like based on the results from Birol-Monteiro formulation, if Y is second order critical point of the problem and Y is rank efficient, then Y will be the global optimal solution for the problem. And here in this slide, I'm comparing ManyDSDP with CSDP on different instances, where here you can see N is the size of the SDP problem, M is the number of the constraints, and R is the rank of the expected rank of the solution. And you can see here, like CSDP managed to solve this problem easily, and this is kind of expected because the size of the SDP problems are not huge for such an interior point method. However, we can see also that ManyDSDP is struggling, especially when we are increasing the rank of the solution. Despite that, CSDP is using ManyDSDP is using the low rank factorization method. And also here we try to track the evolution of the rank of the solution during the ManyDSDP iterations. And you can see here, for example, for this instance, that the ManyDSDP managed to find the correct rank, and then it spends a lot of iterations to reach the feasibility of the problem, to reach the global solution. Also, we tested the same examples with the similar sizes, but with rank one instances. And you can see here now MongoDB is doing better compared to CSDP and compared to the high rank instances with the same size. And here it's clear that these rank one instances are much more easier for MongoDB. And we can see here also like increasing the rank is leading to more iterations and long running time process. And based on these previous results, we start thinking about exploiting the structure of this problem and think a more compact parameterization of the problem of this matrix S or moment matrix. So when we are going to work with the full SDP method, S will be of size n, and so we'll have like n square variable. For low rank SDP, we will have like n times p variable, and with the parameterization of S by Vandermonde matrix, we are going to reduce the number of the variables to v times r, where v is the number of the polynomial variable that we start with, and r is the target rank. And you can see here, like in this example, with taking n is equal to 231, p equal to 20, and v equal only 2, and r equal to 20, for example. And you can see here the difference between the number of variables in every model. However, this huge reduction comes at a cost, which is that increasing the nonlinearity and non-complexity of problem. Because you can see here, like in this Vandermonde matrix, you can see here the coefficients now are becoming nonlinear. And now our SDP formulation is becoming an SDP problem, but with nonlinear constraints. And for this, we used an adaptive nonlinear solver, which is Nitro from Artelis, in order to solve this problem. And the purpose of this test is to see if this compact formulation of the SDP problem is consistent and can converge or not to the solution. And also, we want to see if it can be competitive with the low rank and the full SDP formulation when we are increasing the dimension. And so here I'm comparing this Vandermonde decomposition using Artelis Nitro, and the results of MongoDB is for the low rank approximation, and CSDP is using the full SDP formulation which is the convex problem. And you can see here, like Nitro is overperforming MongoDB on these instances, and also it is competitive with CSDP, and especially when we are increasing the size of the instances. And also, despite the nonlinearity and non-convexity of the problem in the problem solved with Nitro, the solver managed to solve the problem to the optimal solution. Currently, we are trying to study this and see if we can obtain such a certificate for solving this kind of problem to optimality as done in the Burr material formulation. But these results suggest that this direction of focusing on this Vandermonde decomposition problem is promising, and it can be competitive, especially when we have larger problems compared to the full SDP formulation. So to conclude, the tensor decomposition problem can be reformulated as a moment matrix completion problem, which is a convex problem. And you can see here, like using the dual formulation of the problem is much more cheaper than using the primal shape problem. And despite the fact that MongoDB exploiting the low rank structure of the problem, our experience shows that increasing the rank makes the problem much more harder for the solver, and also this solver is much more comfortable with small rank problems. And the Vandermonde decomposition structure can be solvable with Nitro, despite the nonlinearity and non-convexity of problem. As a future work, we are aiming to study more this structure and see if we can have such a certificate or such a validation to work with this parameterization. These are some references that I use in my work. Thank you for your attention.